And this, friends, this is resonance. Hey there, OChemNinjas. In this video, I'm going to explain what resonance is. I'm not going to show you how to draw resonance contributors or explain a resonance hybrid or use curved arrows. Those are other videos. I have an entire playlist on resonance that I'll link to down below. Here, we're just going to define what is resonance. And to do that, we'll go back to GenChem and look at the molecular formula C₂H₄. In general chemistry, you were given a molecular formula and you were asked to draw a Lewis dot structure. You could probably do that for a molecule like this, but I want to go very slowly and very specifically and look at all the rules for drawing a Lewis dot structure from a molecular formula. When we look at the implication of all the rules, not skipping over any of them, that will help us define what resonance means. If you remember the first rule of drawing Lewis structures from molecular formulas, first we need to count up all of the valence electrons in the molecule. Carbon has 4 valence electrons around it in its neutral ground state configuration, and there are 2 carbon atoms in the molecule. Hydrogen has 1 electron in its neutral ground state configuration, and there are 4 of those. That gives us 8 plus 4, a total of 12 valence electrons in this molecule. The next rule for Lewis structures involve the central atom. Carbon must be the central atom. It's the only heavy atom in this molecule, and we must be bonded to the other carbon atom in this molecule. Then we can apply the hydrogens around the carbon atoms. We can put 2 hydrogens on the carbon on the left and 2 hydrogens on the carbon on the right. That incorporates all of the atoms and all of the sigma bonds in the molecule. Do you remember what we do next? Next, we look at the number of sigma bonds and the number of valence electrons and see if there are any electrons remaining. There are 5 sigma bonds in this molecule totaling 10 electrons, so there are still 2 electrons unaccounted for in this Lewis structure. Now, you might be able to see that each carbon is making 3 bonds. Carbon needs to make 4 bonds, so the best thing to do would be to place a pi bond between those 2 carbons for those final 2 electrons. And that's true, but that's not technically the next rule in drawing Lewis structures. Do you remember what the next rule is supposed to be for drawing Lewis structures? After adding all the sigma bonds, the next rule for drawing Lewis structures is to take remaining electrons and put them as lone pairs on the most electronegative element. We don't have any highly electronegative elements, so we could put a lone pair of electrons on one of the carbon. These are the 12 electrons in the molecule. This is technically the next rule in Lewis structure. And so I would ask you, what's wrong with this Lewis structure? Well, to start, we're missing formal charges. If this carbon wants 4 electrons and it owns 5 electrons, this carbon would have a negative charge. And if this carbon wants 4 electrons and owns 3 electrons, this carbon would have a positive charge. But once we get these carbons in place, what's wrong with this Lewis structure? I would submit to you that nothing is wrong with this Lewis structure, and that's going to be an important point when we define resonance contributors. There's nothing wrong with this Lewis structure. It's unstable. It's not the most stable configuration for this molecule, but there's nothing illegal about this Lewis structure. But we know, we've talked about this before, you can probably already see that it would be better if we could take this lone pair of electrons and use it to form a pi bond between those 2 carbon atoms. That would form a different structure where we have a double bond between those 2 carbon atoms and the 4 hydrogens around the periphery. This is an alternate Lewis structure for the same molecular formula. Both of these are valid Lewis structures for this formula. And this, friends, this is resonance. This is what we mean by resonance. Resonance are valid Lewis structures for the same molecular formula with one important caveat. And that caveat is the sigma bonding network for both structures must be exactly the same, and the only difference can be in the placement of lone pairs and pi bonds. This is the definition of resonance. The same Lewis structure where the only difference is the placement of lone pairs and pi electrons. We denote that these are resonance contributors with a special arrow, an arrow that has a point on both sides of the stem. This is a resonance arrow. We use this arrow to separate resonance contributors, 2 Lewis structures that are otherwise identical in sigma bonding network and only differ in lone pairs and pi bonds. This arrow shows that these 2 molecules are related to each other by being resonance contributors. Further, by convention, we bracket resonance contributors in square brackets to show that this series of molecules is related and that these are resonance contributors. In fact, I'm going to tell you later that these are actually not really distinct structures. These are the same structure drawn twice. So in this simple example, we've uncovered a deep truth about resonance. We can have 2 Lewis structures for the same molecular formula that have the same sigma bonding network and only differ in placement of lone pair and pi electrons, and that makes them resonance contributors. This is what it means to be resonant. I need to make one last very important point before we finish this video. I haven't talked about resonance hybrids yet. I have a separate video about resonance hybrids that I'll link to down below, but I want to mention this here while we're getting the definition out of the way. And what I want to make clear is that neither of these resonance contributors actually exists. This is a very important point that you have to embed in your soul. Neither of these structures actually exists. That's why we use the special arrow here. We did not use an equilibrium arrow. These 2 molecules are not in equilibrium with each other. These 2 molecules are not oscillating back and forth. It is not sometimes this structure and sometimes this structure and sometimes lone pairs over here and sometimes it's a pi electron. These are not unique structures. These are not two different structures. Neither of these molecules actually exists. The only thing that exists is the resonance hybrid, and that's the subject of a different video. But I want to say right here, as we're drawing these structures, I want you to get in your mind right now, neither of these structures actually exists. When we talk about resonance, you need to know, neither of the resonance contributors actually exist. The only thing that exists is the resonance hybrid. So that's it. Resonance is defined as a series of Lewis structures that are otherwise identical in sigma bonding, but only differ in the location of lone pairs and pi electrons.
Thanks for training with us today, Ninjas. Check out this other content to see if you can level up even further. As always, don't forget to like and subscribe.